Greetings everyone, this is Mr. Mull, and in this podcast I'm going to talk about the sinusoidal nature of simple harmonic motion. So as you look at this, this turntable here, imagine for a moment that you're watching an object go around on a turntable. Okay, it could be a ladybug or something on some kind of spinning platform. So that little black dot is showing an object as it goes around in uniform circular motion. And I want you to imagine for a moment that if this were on a table and you're looking straight down at it, that you get kind of horizontal with the table. Okay, so you're gonna get down and look horizontally at what's going on. And when you do this, okay, so we'll draw little eyes here. So when I look from the side, I'm going to notice that when the ladybug is kind of back at the back end, it's going to go through the center of the table, and then it's going to go to the left side of the table. And as it comes around the front, I'm going to see it go to the right side of the table. And so if I look at purely where the bug is moving in my line of vision, I'm going to actually see what you see on this blue line here, and that is where the bug's position would be on just the x-axis as I kind of looked across horizontally as this bug went around on this platform. So if I plot this on a graph and I look at this as a position and this is a time, and I look here and this starts at A, which would be the amplitude of this wave function, and then down here would be the negative amplitude. I can actually mathematically figure out that this is going to be a sine or a cosine curve depending upon where we start. And so we're going to be talking about an equation that the book goes over on page 445 that gives you an equation to represent the position of an object in just the x direction as a function of time. Okay, so let's go ahead and talk about that. And so this is true for any object that is oscillating with simple harmonic motion. And any object oscillating with simple harmonic motion will move as a function of time according to the following equation. Okay. Now the book on page 445 includes period in the equation. Now remember, frequency is just the inverse of the period. So if I replace that 1 over t with frequency, what you get is a version of this equation which you're going to have to just memorize this format. And that is x is equal to a cosine 2 pi ft. Okay. Now the book goes through the derivation of how this equation was arrived at, but basically it's the cosine function for the position x as if you were looking, as this little person's looking at the object moving back and forth along the table. And you'll notice this picture down here. This is you looking horizontally, and you'd be watching that little ladybug basically just be going back left and right from your perspective, where the position away from the center would be the position x right there, and then A would be the maximum possible displacement of the bug, which would be kind of the peak of that sine function. So in this equation we have x is our position of the object, a is our amplitude, okay, of that wave function, f is our frequency, and you can see where that frequency came in from the book's version, and then of course t is our time. And so when I look at this equation here, you will find this equation on your equation sheet. Okay, so this is fair game for using this one here. Now another form that you might see is, let's go back. Another form that you might see is the sine version, depending upon where you're looking at this. And the sine version is the exact same, except it's just sine instead of cosine. 2 pi ft. Okay, so I'm going to go ahead and show you how we're going to use this equation. So here's an example problem. It says a 0.5 kilogram object is attached to a spring of a spring constant of 30 newtons per meter and released from rest at a time of 0 from a position of 0.25 meters from equilibrium. And so, you can imagine we have a little spring on here, and there's some equilibrium position, and this object is released 0.25 meters away from equilibrium, and then it's allowed to oscillate back and forth. Okay, and so we're going to be looking at the because this object is moving in simple harmonic motion. I can use this equation that we just wrote down a second ago. So x is equal to a cosine 2 pi ft. And so this question says, find the equation that describes its x location as a function of time. So we're looking for a very specific equation for this exact pendulum mass system. And so what I'm going to do is I'm going to look at the given in the problem that it starts 0.25 meters from equilibrium. And so when I think back to what this would mean about an object that's moving on a spring, that's going to be its maximum possible displacement. In other words, that's going to be my amplitude, which I'm going to plug in for A. Okay, when I plug this into my equation. So x is equal to, my amplitude is 0.25 meters. And then I'm going to go ahead and plug in cosine. And then I have, cosine would be 2 pi. And then we have 1.23. And that's going to be, well actually, we're going to have to get that, times time. And we're going to need to figure out what this frequency is here. Now, the problem doesn't actually tell us the frequency of this oscillating system. So that's where we're going to have to go back to our equation for the period of a mass spring system. Okay, so period, of a mass spring, equation. And so this equation is going to be Ts, this is exactly how you see it on your equation sheet, 2 pi times the square root of m, where m is the mass. And so we want to find the frequency of this equation. Now frequency is, of course, the inverse of the period. Okay, so if I think of, okay, well, my frequency is just 1 over the period, I need to take the reciprocal of this entire quantity. And so when I take the reciprocal of 2 pi, I get 1 over 2 pi. And then when I take the reciprocal of this square root function, we're just going to flip around k and m. So we get k over m. And now I can use this, this equation here, and when I get the reciprocal, I can find the frequency. So I'm going to go ahead and plug in my numbers. 1 over 2 pi times the square root of the mass, or excuse me, the spring constant k was 30 newtons per meter, divided by the mass of 0.500 kilograms. And when I plug all those in, I'm going to get my frequency, which is in the unit of hertz, 1.23 hertz. And so once I know the frequency, I can actually plug that back in here for the frequency of 2 pi times 1.23. I don't even need this thing on there. Let's leave that there. 2.13 times t. And then now what I can do is I can just multiply 2 pi times 1.23, and I'm going to rewrite this equation now here as x is equal to 0.25 cosine of 7.73 t. Okay, this is going to be an equation that would model for me the position of this pendulum. So I could plug in any time I wanted, and I could find the exact position, x position of the oscillating object. Okay, so now what I want to do is I want to show you an example of how we could, another example of using this equation, and this is example number 2. So in this example it says the motion of a particular particle is, particular object is described by the following equation. So they give me this equation on here, x is equal to 0.5 sine, and then they have 1.5 pi times t. And now it's asking me to use this equation and to figure out some information about the oscillating object. And so the first one's really easy. Find the amplitude of the motion. And so I see that they're using a sine function. That's totally fine. The equation's basically the exact same. X is equal to a times sine of 2 pi ft. And so when I look at the way the equation's set up, that first number before the sine is just a. So the amplitude of the motion is just going to be 0.5 meters. That's going to be the first part of the equation. Second one says find the period of the motion. And so when I look at what the problem gives me, I'm looking back at what's here, and I'm looking back over to my original form of the equation because I know it's in, I know that it's this sine function, it's simple harmonic motion. I know that whatever in front of that t, it has to be equal to 2 pi f. So I'm going to take whatever's in front of that t, and I'm going to set it equal to 2 pi f, because those are both going to be equal for this, those are going to be equivalent. So 1.5 times pi is what's written before the t, and that's going to be equal to 2 pi f. Okay. So once I've done this, I can get f by itself, divide both sides by 2, and then divide both sides by pi, and then I'm going to be solving for f, and my frequency is going to be equal to 0.75 hertz. And so once I know my frequency, it asks for the period. All I need to do is just take, of course, the reciprocal of the frequency, and that's going to be equal to 1.33 seconds. And we can actually figure out the period of motion for the object just by looking at this information here. The last part says find the object's position and speed at a time of 1 second. So now they actually want us to find exactly where the object would be after a second passes. So I look at my original equation, x equals 0.5 times sine of 1.5 pi. And then we're going to plug in for t, we're going to plug in 1 second. So I plug in 1 second. And now I'm going to go to my calculator and make sure my calculator is in radian mode, because we are using not degrees here, but we're actually using radians, 1 pi radians. So calculator is in radian mode. And so once I go back and solve for x, and I'm going to find out that x is equal to 0.5 meters, and it's going to be negative. And so that means that as I'm watching this object, it's on the other side of where it started. And so negative 0.5 meters is the current position after a second passes. And then the last one says find the speed of the object at this time. Now the book has a quite elaborate dealing with, especially on page 447, of some more advanced formulas dealing with velocity and acceleration. And those equations will not be listed on the equation sheet. It's likely they're just going to ask you some of those key points in simple harmonic motion where the speed is 0, or the speed is at its max, or the amplitude is at its max. So those specific points on the wave function. So if I'm thinking about this wave moving along, and it started at 0.5 meters was the amplitude, and now it's at negative 0.5 meters. What this means is it's actually the farthest away from the equilibrium position. It's all the energy is back stored in the spring. So if I think of my energy conservation ideas, where the mechanical energy initial is equal to the mechanical energy final, initially, if I'm thinking of my spring as being fully displaced from equilibrium position, we're looking at it's having its elastic potential energy, which is going to be 1/2 Ka squared is the maximum amount of energy initially, where we pull back our spring to a set amplitude and then let it rip. Okay, so this is kind of our full energy situation. I'm trying to add room here. Full energy situation at the beginning. So when I look at the final energy situation, whenever we're dealing with simple harmonic motion, it's either in the process of moving or there's still some energy in the spring. That's the only two places that we're going to have energy. It's either going to be stored in the spring, 1/2 kx squared, depending on how much that spring is displaced. And if it's moving at that current point in time, it has kinetic energy, 1/2 mv squared. So if I look at this situation here, where I have my object's position is 0.5 meters, that means that it's at its maximum displacement. So all of the energy is stored in the spring, which means if all the energy is stored in the spring, then there can be none left for kinetic energy, and that's going to be the instant when it's turning around, changing direction. We know that the velocity is actually going to be 0 at that point when it's turning around, and at that maximum displacement from the equilibrium. Alright, this has been a video explaining the sinusoidal nature of simple harmonic motion, and I hope that this was helpful.